Maths educational video, vector functions and motion in space. Let's quickly define a vector function. The name already tells us what it is. It's a vector whose components are functions. We'll consider two cases. First is when we have a function in one variable, and secondly in two. For the case when you have one unknown, either in 2D or 3D space, this is typically representing position of a moving particle. That we will cover in this video. For the case of two variables, this vector will represent a surface in a three-dimensional space. This will be done in a separate video. For motion in space, we have a particle moving in a three-dimensional space and we let t be the time taken. Then obviously the position of the particle must all depend on time. So x, y, and z will all be functions of t. The three equations, one for x, one for y, and one for z, in terms of their component functions, are known as parametric equations. And t is called the parameter. We can write these three equations in vector form, giving us the so-called position vector of the particle. And this position vector is a vector function that we saw earlier. Here's a quick example to tell you that vector functions are not entirely new to us. In the course of vectors, we have learned this. The equation of a straight line in three-dimensional space is given by this expression. The first vector is any points you know on the line. Second vector, MNP, is the direction vector of the line. Let's talk about differentiation of a vector function. It's done through a so-called component-wise differentiation, which means you differentiate f, g, and h respectively to get the x, y, and z coordinates of r'. In the context of motion of particles, this vector is called the velocity vector of the particle. That's because we are differentiating the displacement. More on the velocity vector. As you know, vector has direction and magnitude. So the direction of the velocity vector gives us the direction of motion of the particle. And it turns out that the velocity vector is tangential to the path of the particle. As for the magnitude of the velocity vector gives us the speed of the particle. We can further differentiate velocity to get the acceleration vector that we all know from kinematics. And again, it's done by component-wise differentiation. Let's talk about tangent lines. Suppose we wish to find the equation of this green line, the tangent line, to the path of the particle at a given point. So let's call this point P when t equals to t0. So t0 is any given time. We just saw earlier that the velocity vector is tangential to the path. So the direction vector for this green line is given by the velocity vector. And together with the point P, we can write down the equation easily, the one in the box. We end the video with an example. Here we are given a curve of a particle and we are asked to find the equation to this curve at the point t equals to 1. Based on the formula given, we need to find two vectors. The first is the point and the second vector is the velocity vectors. First, the point. This is done easily by substituting t equals to 1 into rt, the position vector, to get r of 1. So this is a point on the line. As for the velocity vector, we differentiate r component-wise, substitute t equals to 1. So this is the required equation of the line. We also asked to find the speed of the particle at t equals to 1. As we know, is simply the magnitude of this vector. So we will get the square root of 11.